All right, get ready, because today we're going deep, really deep, into the world of physics research, quantum gravity.
Oh, quantum gravity, always a fun one.
It is. And we've talked about quantum mechanics, that's for the really small stuff, and general relativity for the universe at large.
Two incredibly successful theories.
Exactly. But when those two worlds collide, well, that's when things get really interesting, wouldn't you say?
What gets me is we're talking about two of the most, if not the most, successful theories in physics, and yet they just seem fundamentally incompatible.
They really do.
On one hand, you have quantum mechanics, perfectly explaining those tiny particles, the smallest scales, and then you have general relativity, describing gravity, the large-scale structure of the universe,
Yeah.
but getting them to play nice. That's the real challenge.
It's the biggest challenge, I think, in physics right now. Because we need a theory, right? A theory that can deal with the very small and the very large all at once.
The theory of everything.
Exactly. And right now we have two main contenders, two heavyweights in the ring, string theory and loop quantum gravity, LQG.
Both very different approaches.
They are. So string theory, I think a lot of people have at least heard of string theory. What's the quick explanation?
Okay, so just imagine, you could zoom in way beyond protons and neutrons, quarks even, the tiniest particles we know.
This is beyond.
Exactly. And you'd find that, surprise, it's not point-like particles all the way down. Instead, it's these tiny, and I mean T-I-N-Y, vibrating strings of energy. These strings, they vibrate at different frequencies, and those frequencies, they determine a particle's properties, mass, charge, the whole shebang.
Okay, so it's not just a bunch of tiny rubber bands bouncing around. There's more to it.
A lot more. But that's the basic idea, yeah. And the beauty of it, this elegance of string theory, it's this potential to unify, to bring together all the fundamental forces of the universe.
That's a big deal.
QGE.
Okay, so we've got vibrating strings. I think I'm with you so far. But now let's go to maybe less familiar territory, loop quantum gravity, LQG. What's the core idea here?
So a completely different approach, right? Instead of this smooth, continuous space-time we're used to, LQG says, nope, space itself is made up of tiny, indivisible chunks. Imagine pixels on a screen, but vastly, vastly smaller.
A pixelated universe.
Basically, these pixels of space, these loops, are the fundamental building blocks in this picture, the foundation of reality.
That is a pretty radical concept, I gotta say.
Absolutely radical. It challenges everything we thought we knew about space and time. It's suggesting there's a limit, a smallest possible unit of space. You can't go any smaller.
And this is where things get even more interesting, right? Because even within the world of loop quantum gravity, there's debate.
Oh, absolutely. Tons of debate. That's science for you.
This is true. This is true. But the big debate here, it's about whether we can even test this theory.
And that's what makes LQG so fascinating, so challenging.
So which side are you on? Can we test it or not?
Well, let's just say it's a bit more nuanced than a simple yes or no. On one hand, you have physicists like Carlo Rovelli, brilliant mind, and he argues that, look, even if we can never directly observe these loops, LQG still gives us this incredibly valuable framework for understanding quantum gravity.
So it's valuable just as a thought experiment, even if it's not right. Is that what he's saying?
In a way, yeah. But then on the other side, you have physicists like Lee Smolin, and he's more of the mind that, hold on, a theory isn't really science. Not truly, unless we can test it.
Even if those tests are really hard to design.
Exactly. It's this fundamental question. Is it enough to have this beautiful, elegant theory on paper? Or do we need that connection to the real world, to evidence?
So it's not even really about right or wrong at that point. It's, are we even playing the same game as science?
Precisely. And this whole debate, this isn't just an LQG problem either, right? This pops up in other areas of physics, especially when we're talking about unifying quantum mechanics and general relativity.
Makes sense, I guess, if your brain is already going there.
Right. Like, these are big questions. But some other examples. Well, let's talk about string theory for a minute.
Oh, string theory. Everyone's heard of string theory.
Exactly. It's been around for decades. But one of its more, shall we say, interesting features is that it needs extra dimensions to work.
Wait, extra dimensions like beyond, up, down, left, right, we're adding more directions.
That's the idea. Not just 3 spatial dimensions, but more. Maybe 6, maybe 10, depending on the flavor of string theory you're tasting.
Okay, my brain is starting to hurt a little.
That's understandable. But the idea is that these extra dimensions are curled up really, really small. So small we can't directly observe them.
Okay, so how do we even know they're there?
Well, that's the thing. String theory says we might be able to see their effects indirectly. maybe through how gravity behaves at very, very tiny scales, or by looking for these tiny vibrations, evidence of the strings themselves in the cosmic microwave background radiation.
That's the afterglow of the Big Bang.
Yeah, you got it.
Yeah.
So basically, testing string theory, it's more than just building a bigger microscope. We need to get creative.
I'm sensing a theme here. Big ideas, even bigger challenges when it comes to actually proving them.
And then there's supersymmetry, which throws in the idea that every single particle we know of in the standard model has a partner particle we haven't met yet.
So, like a whole other set of particles just waiting to be discovered. Why do we even think that might be a thing?
Great question. Supersymmetry is really elegant in a lot of ways. It solves some problems we have with the standard model. Like it helps explain why the Higgs boson has the mass it does and helps bring together the strengths of those fundamental forces at high energies.
High energies, like in the early universe.
Exactly. But here's the catch. We haven't seen any of these partner particles, not
Yeah.
a single one, even at the Large Hadron Collider, which smashes particles together at crazy high energies.
So another theory, another set of missing pieces.
Pretty much. And we can't forget about inflation theory. Remember that one? It tries to explain how the universe expanded so quickly, so rapidly, right after the Big Bang.
Right, like it went from 0 to 1 billion miles an hour in a fraction of a second.
Faster, even. And inflation theory is important because it helps explain why the universe looks the way it does today, with its large-scale structure and that evenness of the cosmic microwave background radiation.
But there's always a but, isn't there?
Of course. Because, just like our other theories, it relies on, you guessed it, particles and fields we haven't directly observed yet.
So to recap, brilliant minds, amazing theories, very few ways to actually test any of them. It all sounds very impressive, but why should someone who isn't, let's say, a theoretical physicist care about any of this? What's the big takeaway?
That's the million-dollar question, isn't it? And honestly, it's something physicists are wrestling with too. Science is built on this idea of testable predictions. That's how we know what we know. But when theories get so complex, so removed from what we can observe, we have to ask, are we drifting into mathematical fiction?
So again, not even right or wrong, just are we even doing science anymore if we can't test it?
Exactly. And historically, physics has been this driving force for technology. Think electricity, magnetism, computers, lasers, all those came from experiments, observations, testable predictions. But if physics loses that connection to the real world, to what we can see and measure, well, its ability to push those boundaries, to drive progress in other fields, it's at risk. So it really begs the question, has physics, in trying to find these elegant, beautiful theories, strayed too far from its roots?
So we're so busy building these incredibly detailed pictures of the universe in our minds that we've forgotten to check if they actually match up with reality. It's a little, I don't know, unsettling to think we might be working off a map that's completely wrong.
Yeah, I get that. But I wouldn't say we're totally off track. Science has this way of, correcting itself, right? These debates we've been talking about, testability, the role of experiments, they've been around forever.
So physics is just going through a phase. It'll come back to the lab eventually.
Something like that. In the end, theories, they need evidence. Even if it's indirect, we need something to back them up, or they just fade away. That's how the scientific method works. It's messy, but it sorts things out.
Okay, that makes me feel a bit better, I have to admit. But just for a second, let's say we do want to test something like loop quantum gravity, those loops, that pixelated universe. What would that even look like? Where do you even begin?
The million-dollar question. We're talking about scales so small that, honestly, our best instruments right now, they're nowhere close. We need a whole new way of looking at the universe.
So forget a bigger collider. We need something completely different.
Way different. We might be talking about searching for these tiny quantum gravity effects, but on a massive scale, like looking for how they change light coming from the very, very early universe. Fractions of a second after the Big Bang, kind of early.
Talk about a challenge, looking back billions of years to see something unbelievably tiny.
Or we might need to get even more extreme. Maybe the only way to see these effects is by studying black holes. I mean, that's where gravity is at its most intense, right?
So basically, we need to go to the most extreme environments in the universe just to get a glimpse of these fundamental building blocks.
It's a long shot, for sure.
Yeah.
But that's also what makes it so exciting. This is pushing the boundaries of what we know, what we even thought was possible. It's going to take creativity, new technology, and a whole lot of really, really smart people.
Well, I'm glad those smart people are working on it, because my brain is officially fried. So where does that leave us? We've gone from the smallest particles to the edges of the observable universe and uncovered a bit of a, let's call it a midlife crisis in physics.
Haha. Yeah, something like that. But the most important thing, we have to keep asking these questions. We can't be afraid to push those boundaries, to challenge what we think we know, because that's how we get closer to the truth, however strange it might be.
And who knows, maybe one of our listeners will be the one to figure it all out. They'll be the one to finally crack the code of quantum gravity. But until then, keep those minds curious, and we'll see you on our next deep dive into the universe and all its mysteries.